A very good evening to all of you. So today we will be solving some numericals on the power amplifier. As you know that the power amplifier is an amplifier which transfers the maximum power to the load. So we have seen some classification of the power amplifier depending upon the location of the operating point. The first one is the class A amplifier, the class B amplifier, class B, then class AB power amplifier, and class C power amplifier. So in class A power amplifier, we have studied two power amplifier. The first one is direct coupled, and the second one is just a transformer coupled class A power amplifier. Now, why we have shifted our attention to the class transformer coupled class A power amplifier is because of the poor efficiency of the normal class A amplifier. The efficiency was around 25% in the class A power amplifier, which has been slightly improved by it has become doubled. I think the efficiency is around 50%. So why there was a problem in the class A power amplifier, there was the resistance RC. You can see there was the collector resistance RC, or you can call it as the load resistance. That is, load resistance was there. So even if you are not applying any input signal, the current will still flow through the resistance because of the DC biasing. DC biasing will remain constant for entire operation, and you know that the AC value is going to vary like this. So even if you are not applying any input signal, that time you are also having the DC biasing voltage. You can see from the output characteristics of the transistor, that is the common emitter transistor, and this is IC. So we will draw the load line first. So these are you can see this is VCC, these are the coordinates, and this one is VCC upon RC. So in the class A power amplifier, the operating point is at the middle of the DC load line. So even if you are not applying any input signal onto the DC operating point, still you are going to have this much finite collector current, and this finite collector current will pass through a resistance, and because of that there will be IC square into RC loss. Now this is the power dissipation in a transistor, which will contribute to the in lowering the efficiency. So this was the problem. So we have to eliminate this problem using a transformer. So now you can see here the RC is replaced by the transformer. You can see how the RC is replaced by a transformer, or you can call it as the load resistance also. So you can see that you have introduced a transformer and you have shifted your RL from this point to the this point. So now you can see that there is no connection between RL and VCC. You are having N1 and N2 as primary and the secondary turns respectively. So in this way, you can increase the efficiency by nearly 25%. So the efficiency of this transformer coupled is 50%. So now you can see this is the actual load resistance, and this one is the reflected load resistance. We have seen this in the lower classes. That you can reflect the load impedance in the primary side. Normally you can see that in the transformer you are having two important sides. This is the primary side we can consider, then there is a core, and there is secondary side, and to the secondary side we have connected a load. Now in this case, why we have connected on the secondary? Because we don't want that biasing voltage should come in contact with the RL. So in that case, it if it was connected with the VCC, then the collector current would flow through the RL, and there will be a power dissipation. So to avoid that condition, we have used a transformer and we have shifted our RL from primary to the secondary. But the entire thing, the entire, you can see the configuration is in the primary. So it means that you will have to create a reflection on the primary side. So what is that reflection will be? That reflection will be RL dash, RL dash. I think this RL dash is now this RL dash is now in the primary side. So we will just write this is N1, this is N2, then this is V1. We will assume the current which is flowing through the primary of a transformer, we can consider it as the I1. Now similarly, you can, this is I2, because you will have to feed the load resistance. That is why the current is directed into the load resistance, and this is V2. The V2 is the output voltage of the load, and V1 is the voltage of the source. So suppose if you want to write the equation of the reflected load impedance in terms of RL, then how you are going to write? Now RL dash will be equals to what? V1 upon N1. Fine. So now you will have to write in terms of this. You can say. In terms of RL, so we know the relation, that is voltage is directly proportional to the number of turns, and you also know that the power will remain constant when you are transferring a power from primary to the secondary. So from this you will get one relation, that is V2 upon V1 will be equals to N2 upon N1. So voltage is directly proportional to the number of turns. So V2 will be equals to N2 by N1. This is the thing. Now similarly, you can also write V1 I1 will be equals to V2 I2. So in that case, V2 upon V1 will be equals to I1 upon I2 will be equals to N2 upon N1. Fine. I think this relation is already discussed in the classes. Okay, so now coming here, I'll be writing here because there is no space left for me to write the things. So RL dash will be, so now everything should be written in terms of secondary. So V1, so you will, how you are going to write V1. So just take it out, then just V2 upon V1 will be equals to N2 upon N1. So suppose if you want to write V1, so that one will be V2 into N1 will go on the top, right? So that is N1 upon N2. Okay, so now we will be writing V2 into N1 upon N2. Now similarly, how you are going to write I1? I1 will be written as what? I1 I2 into N2 by N1. Fine. You can see here I1, how you are going to write this I1. So I1 will be equals to N2 by N1 into I2. So okay, coming here, so I2 into N2 by N1. Fine. So RL dash will be equals to V2 upon I2. If you just move this upwards, then what is the value? That is N1 upon N2 ka whole square. Fine. And what is V2 upon I2? What is V2 upon I2? You can just look here. V2 upon I2 is the load resistance. You can apply here Ohm's law simply because the load resistance there, so you can simply apply the Ohm's law there. Fine. So now RL dash will become RL into N1 upon N2. So this is the turns ratio we have obtained. I think the first you will have to find the turns ratio only. So I think you have got this concept here. You will have to just shift the value of load resistance onto the primary, and RL dash will be equals to V1 upon I1. To calculate, to write RL dash in terms of RL, you will have to take the help of two equations. The first equation will be voltage is directly proportional to the N, and the power which is flowing from primary to secondary will be a constant value. because your transformer will be acting as a mediator. It is not, it will never act as a load. So in that case, power and the primary and power in the secondary will be constant if you have assumed an ideal transformer. Now V2 upon V1, V2 upon V1 will be equals to I1 upon I2 will be equals to N2 upon N1. So V2 upon V1 will be equals to N2 upon N1. So V1 will be equal to this value, and similarly you have written I1 in terms of N2 upon N1. So this is the thing, that is RL dash will be equals to RL into N1 upon N2 ka whole square. So I think this is the thing. So now, okay, just a minute. I'll be just a minute, right? Thank you. Okay, so now this is the N1 upon N2. Okay, so now we coming down to this problem. A transistor having a collector breakdown voltage 40 volt. Now you can see here the collector breakdown voltage, that is the maximum voltage we are discussing here, and the maximum collector current of 0.8 ampere. Fine, the collector current is having a maximum value of 0.8 ampere, is to be used in a class A transformer coupled amplifier to drive a 4 ohm load. So you can just see that the uh, load is RL. This is a 4 ohm. This is a 4 ohm, right? Uh, so when this is a transformer coupled class A amplifier, you can see that your operating point will be like this only. We have already discussed in the class that in the class A power amplifier, your operating point will be, this is VC. Now this one is VCC by 2 and VCC upon twice into RC. Already discussed in the theory class. Uh, so now when the VCC is directly connected to the collector, so in that case the collector current will be IC only. So it means that this is IC, this one will be twice IC, and this one will be VCC. So this is twice VCC. This is twice VCC. Okay. Hmm. So now you will have to see the maximum value of the uh, the maximum value of the voltage and the maximum value of the current. Fine. So now coming down to here, this is the output characteristic. You can see that this is peak to peak value, or this is peak to positive peak to negative peak value. So what we can write, V peak to peak will be equals to how much? This is twice VCC, and V peak will be equals to VCC. So this is the maximum value, that is VCC. Or you can see that this is the breakdown voltage. Breakdown voltage, it means that if you apply a voltage above the breakdown voltage, then in that case your transistor will damage. So here, what is the maximum value? So from this figure, you can say that maximum value is VCC only. Now, similarly, the maximum value of current will be what? Maximum value, this is peak to peak. You require only this much. So that one will be IC only. So you can easily say that maximum value is V max will be equal to VCC. So what is given here? V max will be equal to 40 volt. V max, so we can say that V max will be equals to 40 volt, and Im will be equals to 0.8 ampere. So now you will have to calculate the turns ratio. So how you are going to calculate that thing? So RL dash will be equals to what? See, entire thing will be on the primary side. So that's why we will have to take into account only RL dash, not the RL. So RL dash will be equals to what? VM upon IM. Fine, because when you're applying a maximum voltage, it means that maximum current is bound to flow through that. So Vm upon Im, that is 40 upon 0.8, that one will be 50 ohms. Now you have got the equation. Just now we have derived this equation. RL dash is equals to N1 upon N2 ka whole square into RL. Fine. So RL dash will be just now calculated 40 upon 0.8, that is 50, and N1 upon N2 ka whole square, this is 0.4. So after substituting all the values, will come down to this. This is, sorry, I think this is just a minute. This one is 4 ohms only. I thought this is 0.4. This is 4 ohm only. So N1 upon N2 will be equals to under root of 50 upon 4. This is 3.53. 53 N1 upon N2. So now you will have to calculate the what is the maximum power delivered to the load. You can see that what is the power which you want delivered to the load, that is the AC power, because the signal which is applied at the base is the input AC signal, and you will have to transfer only the AC input signal to the load, and this should be an amplified one. So in that case, what should be the value? This is VRMS ka square upon RL. Fine. Either you can write VRMS. See, there are three ways. In three ways I can write it. VAC will be equals to VRMS into, this is the maximum value only, maximum VRMS into IRMS. In that case, it will be VM upon root 2 into IM upon root 2. So VM IM into VM IM upon 2. Fine. Then other one will be PAC. PAC maximum will be equals to, just a minute, hold on. PAC RM equals to, okay, my mouse got stuck. So VRMS square upon RL. So in that case, it will be VM upon root 2 ka whole square upon RL. So you can write VM square upon twice into RL. Fine. So we'll see which value. This is VRMS square upon RL dash, right? Because everything will be on the primary side. So this you will have to take into account. That is 40 square upon 2 into 50. So you have got this value. Now the next part which we have to calculate is supply voltage. Supply. What should supply voltage? Supply voltage is what? Supply voltage is the peak value, na? You can see from this figure only, this is the peak value, and peak value it is already given, that is a 40 volt. Understood or not? This is peak to peak, it is twice VCC. Peak value or a maximum value will be VCC. Then what is the power dissipation in a transformer? So before calculating the power dissipation, you will have to calculate the input power. No? So input power will be equals to what? That is VCC into operating current. Fine. So VCC into operating current will be IC only. So here you can see, from this figure only I am writing. From this figure only I am writing. IM. This is the peak value. IM will be equal to IC. Sorry, or you can say IC will be equals to IM. And what is the value of IM? uh, Iron, it is white. Okay, 0.8 ampere. So this is 0.8 ampere. Now similarly, VCC will be equals to VM. This is 40 volt. That is a transistor having a breakdown voltage. So I think this one will be 40 into 0.8. 4 into 8, 32 watt. We are having input power. So you can easily calculate the power dissipation, because power dissipation will be what? Power input minus power output. So this 32 minus 16, that will be 16 watt. 16 watt. You can see easily. Okay. This problem is very easy. Uh, so now in the next video, we will be solving some more numericals. Thanks a lot for listening.